It's important to keep in mind that there also are some assumptions about the X matrix. Specifically, first, the X matrix is just assumed to be deterministic and known, meaning you know exactly what happened when. There's no probabilistic aspect to it. You might have determined your X matrix in a probabilistic way, meaning you might have used some kind of randomization and jittering to determine the X matrix. But now that it has happened, you know exactly what happened when. But to us, the more important aspect is that no regressor in our X matrix has to be a linear transformation of one or more other regressors. In other words, there ought not to be any multicollinearity. Now, unfortunately, the truth is that it's not much of a question whether there is or there isn't multicollinearity. There almost always is. The question is, to what degree is there multicollinearity? And see, the problem of multicollinearity is that it has two main consequences. First, it decreases the efficiency of the design and therefore degrades power. Second, and the one that we will look at for the most part, the parameter estimation can actually be completely wrong. It can vary greatly and can even end up being in the wrong direction, meaning if you have two regressors and they happen to be correlated, the values that you get in terms of the estimation of the parameter for these two regressors could be completely wrong, could be completely random, could even be in the wrong direction, meaning if you only had one of the two, then you might get a positive number. But if you have both and they're correlated, you might get a crazy negative number. Let me show you what I mean. So here's an example, and these are slides that I got from the wonderful Jeanette Mumford. So say that you have this circumstance, and as you're seeing, regressor 1 and regressor 2 are highly correlated. In fact, they're perfectly correlated. So the reason why this is a problem is because if I told you, hey, you know, beta 1 is 10, what is beta 2? Well, you would know that beta 2 has to be 2. And it would fit perfectly the problem, right? You would have 10 plus 2, and you'd get exactly 12. But there are infinite ways of getting 12. Right? Beta 1 could be 10 and beta 2 could be 2. Beta 1 could be 100 and beta 2 would be minus 88. So now beta 2 went from 2 to minus 88 and it would fit perfectly our data. Beta 1 could be minus 112. What would beta 2 be? 124. Right? If you add them up, you still get 12. So the real problem is that there are an infinite number of solutions for beta 1 and beta 2. And all of these solutions are all equally good. There's no sense in which one of these solutions is better or more real than the other ones. They all are mathematically perfectly fine. Here's an example from the point of view of simulations. So take these two cases. We do a multiple regression, which you're seeing right here. And we have two parameters. We have two regressors, x1 and x2. Under one condition, they are lightly negatively correlated, minus 0.2. Under the other condition, they're highly positive correlated, 0.96. Now, keep in mind that the true value, so these are simulations. So we will give the true value to beta 1 and beta 2. Then we will add noise, and then we'll run a regression and see how well we can recover these values. So beta 1 we know is equal to 2, and beta 2 we know is equal to 4. Okay, we are setting them. Then we will add noise, and we will see how well we can recover beta 1 and beta 2 from, let's say, 100 regressions. And that's what you're seeing here. So on the x-axis, you're seeing the value at each of these 100 regressions for the intercept, so beta 0, or alpha, you might know it as alpha. And then here, you're seeing the values of beta 1 over 100 different simulations under the condition of low variance, which is the small line in the middle, under the condition of x1 and x2 being lightly negatively correlated, so when they're not highly correlated. And that's the red line that you see in the middle. And the same is true for beta 2. However, when beta 1 and beta 2 are highly correlated, then look how much the values that you get at each simulation can change. For example, here, there's this one case where beta 1 is, let's say, just about minus 17, perhaps. Unsurprisingly, at that exact, at that same trial, x2 is close to 20-something. Right? Remember, we know that the real values are 2 and 4. But because x1 and x2 are so correlated, you could get an infinite number of possible values, and they're all equally good. So sometimes x1, beta 1 is down here and beta 2 is up there. Other times, beta 1 is up here and beta 2 is down here. See what happened? In one estimation, beta 1 was minus 18, and another estimation, it was plus 15. Similarly for x2, beta 2 was plus 20 something in one, and minus 11 or minus 12 in another one. The results from estimations when two regressors are so highly correlated can vary wildly. Not only they can vary wildly, they can also be in the wrong direction. If you look at the variance, you will notice that you get low variance in the uncorrelated cases. And obviously, given this, you get really high variance in the correlated cases. And now, how does this affect your t-statistic? It depends. Sometimes you get a better t-statistic out of it. Sometimes you get a worse t-statistic out of it. So the bias here can go in either direction. Now, the most important aspect is that if you take all of these 100 simulations that we've done, and you look at the residuals, they are identical. So the highly correlated and the uncorrelated cases have the exact same residuals. So they're both perfectly fine explanation. The betas that you get are both perfectly fine explanations. It's just in one of the two cases, you can't trust them because there's too much collinearity, right? If you look over these 100 iterations, the variability in the uncorrelated case, this one here, versus the correlated case is exactly the same. Again, the difference is that the parameters themselves you get, those can be completely off. But the fit of the model is just perfectly good.